attention here for just a couple of minutes. Thank you so much. So first of all, yes, there is a little list over here of my friends who I don't have safety contracts for, or you turned it in late and I just didn't get crossed off. So I've got some blank ones if you need one. If you just have one, need to take it home and get it signed, that's fine too. If you have it to give to me, that's great as well. Whatever needs to happen so that I've got it in my file, that would be super helpful. Let me know if you need a new one. I've got some here. Okay, so today, just kind of a heads up. First of all, yes, it is National Cinnamon Raisin Bread Day. So do what you need to with that after class. Is that fair? I know, right? That was kind of unkind. We're going to start with a warm-up problem in just a moment. We're going to finish our discussion of kinematics problems that we kind of ended with on Friday. We're going to go over that workbook sheet 1H, work on homework questions if you have them, do some graph sorting. It's going to be a full, fun physics day today. And yes, you do have some homework for Tuesday as well. So if you need to write that down right now or be reminded of that right now, there it is. Once you've got that all figured out, go ahead and take a look at this warm-up problem. Is it big enough? Can you guys see it from the back, or do you need a little bit bigger? Bigger. Here, I'll just do it this way. Everybody got this stuff? Got your homework written down if you need to? Oh, no. Stop this guy. All right. I'll make it this big for now, and then I'll go over to my other one that I can make really big in a second. All right. So you've got your homework writing down that you're doing, and then taking a look at that warm-up problem. Go ahead and do that. See your boards. Show me what you got. So we're doing acceleration first. I see lots of horizontal lines of varying heights because we have varying scales. Again, I've mentioned this a few times and I'm going to keep mentioning it so you don't forget. Sketch means you do not need numbers, right? It's all about relative sizes. If you put them on the same graph, that's great. If you put them on different graph, that's okay, as long as they're all labeled. So it says two objects start from the same position at the same time. From rest, but with different magnitudes of positive acceleration. So different magnitudes of positive acceleration, that's what we see here. Bam. And so I saw two lines, right? Acceleration of this. Oh, now it's frozen. There we go. And acceleration of this, right? So this one has the larger acceleration, and this one has the smaller. Everybody happy? Yes, they are. All right. You can erase that or just erase the labels in the middle and keep the axes. And go ahead and draw your velocity versus time graph. Velocity versus time graph. You got this. So I'm seeing lots of lines with a constant slope. Is that right? Because if you're accelerating, acceleration means, what does it mean? Change in velocity over time, right? So we've got acceleration is delta V over T. Am I still frozen? No, I'm not. I remember to unfreeze today. Yes. All right. So if I've got an acceleration, that means my velocity is changing. How do I know? I see everybody starting from the origin. Why am I starting from the origin? Because it says that it started from rest. If it doesn't say that, then they could be anywhere along the x-axis, or along the y-axis. Okay? But because it says that, we're going to specify. Now, if I make my smaller acceleration this one here, so this is the smaller one, where does my other one need to be? Steeper slope. Why steeper slope? Because the velocity is increasing faster because I've got a change in velocity over time that's bigger for the larger one, right? So it's going to have a larger, higher slope. Again, I don't care the numbers exactly, but I want the same concept. So a larger. All right. Good. One more. Go ahead and do it. All right. So I see some parabolas, yeah? We agree that if we've got a change in velocity, that means that the slope on the position versus time graph is going to keep changing. Yeah, so I get 1, and it says that they start from the same position. Does it say that they start from an origin? No, could they start anywhere up along this? For sure they could. Yeah, we know how to shift those graphs. It doesn't matter. Usually we like to start things from the origin, but again, you do not have to. But I'm going to go ahead and draw one like this. Okay? And I'm going to say that this is the one with the smaller acceleration. And so again, just to be very clear, for some of us, this makes total sense. We've been doing math like this for a long time. Or, we sit in calculus and they tell us the exact same thing. But if you're not there yet, that's okay. We still love you and we want you to be happy. We just want to look at these slopes. So that slope looks like, oh, hello, that's a very different picture. And then there's one like this. And then can you guys kind of see this? Yeah, let me highlight them so they're a little bit easier to see. So the slope of this curve, the slope of the tangent line of the curve, right, is changing. Okay? That's what we're talking about. So for my math friends that are like, I don't really know what that means. All we're saying is that if we put all of these lines together, they're going to get steeper and steeper and steeper. That means that the velocity gets bigger and bigger and bigger because the acceleration is constant. Okay? So if that's my smaller one, then talk to me about the other one. Is it going to be further in towards the axis or further out towards the x-axis, I should say? In towards the y or out towards the x? In. Why do you say in?
The tangent line will be steeper.
The tangent line gets steeper faster, right? Yeah. The tangent line gets steeper faster, which is exactly right. So we just want to make sure, because they're both going to start from that 0. So they really start from here, right? And this one's going to start from here, but it's going to get steeper faster. Okay. So over time, at any given point, if I was going to look at the tangent line for this one, at this point right here versus this point right here, I've got a steeper slope here. That steeper slope corresponds to a higher velocity, and that higher velocity comes from the higher acceleration. These all fit together, yeah? Fantastic. I hope that even if that seemed really simple to you, that you can kind of get your head around all that happens in this problem. There's a lot of stuff in here to really get, okay? So fantastic. I want to check, I just kind of see where we're at here. So the next thing is that I just kind of ate up that other thing. Finish discussion of kinematics problems. So we were going to do that. So I want you to take a look, pull those kinematics problems out, because I feel like by yesterday I mean Friday, last time we were together, we may have gotten a little bit interrupted in terms of how far we got, but I don't remember for sure. I'm going to be honest. So I want you to take a look back. These are the little quarter sheet that I gave you, or you were given on Thursday by the sub. I feel like we made it through the second one. Did we make it through everything that you wanted to go through, or was there anything left? Go, Eden.
Part B of the last one.
Part B of the last one? Okay, awesome. Did we make it through some of it? I don't even remember here.
Yeah. And now we say chart.
Say again?
And now we say chart, or is that later?
Later.
Later.
Thank you for asking. But yes. I was like, what? What? I get you. Okay. Did we start the last one or no? We didn't. Okay. Okay. Just keep saying it over and over until it. All right. Okay, and you just really want to do the second part, is that right? Okay, so friends, it's been a few days, a few hours since you've looked at this, so let's just get our brains back in here. So car starts from rest, travels for 5 seconds with a uniform acceleration of 1.5 meters per second squared. Is it speeding up or slowing down? Speeding up. Well, it's starting from rest, so probably it's speeding up. Is it going in the positive direction or the negative direction? Positive direction, because we got a positive, right? So the velocity is going to get bigger and bigger in the positive direction. The driver then applies the brakes and causes a uniform acceleration of negative 2 meters per second squared. So is it going backwards now, or is it continuing to go forwards? It's still going forwards, at least for a little while, right? At least for a little while, and it might end up going backwards. We're not sure. We have to figure that out, okay? If the brakes are applied for 3 seconds, how fast is the car going at the end of the braking period? That's not what she cared about. But really, how far has the car gone from the start? Okay, so there are 2 pieces to this story, right? So I'm going to write down my givens in 2 pieces just so that I don't get super confused, because otherwise, sometimes that happens. So I'm going to write my givens down. You can do this too. So we know Well, we know for the first part that it goes for 5 seconds, and it has an acceleration of 1.5 meters per second squared. And that's kind of the first story. Is there anything else we know from the beginning, from the first part of the story? It starts from rest, absolutely. So the initial velocity is 0 meters per second, okay? Sometimes there are those hidden givens that you have to make sure that you find because you have to have 3 things you know to find the one thing that you want to know, right? We're going to do the chart in just a minute. That came to me already. All right, and then the driver applies the brakes, causing a uniform acceleration of negative 2 meters per second. So that's going to be our other set of givens. We have an acceleration of negative 2 meters per second squared. Excuse me. The brakes are applied for 3 seconds, 3.0 seconds, and they want to know the final velocity. Okay. Oh, and then actually what we really want to know, that was really not the question. Really the question is, well, it's how far did it go during this time? I'm going to call this part B. And we also need to know how far it went in part A. Does that kind of make sense? So, because it said, how far has it gone from the start? Can you use this information to find displacement in the x direction? Or excuse me, displacement for part A? I don't know. Some of you are getting your equation sheet out. I want you to get your equation sheet out, and I also want you to get out a piece of paper, because this is where we're going to say, chart. All right. Beautiful. All right. So this is not something that you need to utilize forever, but when you're starting to explore kinematics equations, sometimes it's helpful to get this kind of in your brain. So I'm going to just write down here the equations that we know, the kinematics equations that we know. So we've got Vx is equal to, or I'm going to say Vf. So I'm looking at the yellow sheet. This is the first one that's printed on there. Vf is equal to Vi plus At. We've got, I call it delta x is equal to VIT plus 1/2 AT squared. So you guys could write these down too, because this is going to be helpful in just a second. And then we've got, I'm going to call it VF squared is equal to VI squared plus 2A, I call it delta x. How are we doing? Is that okay? Those things feeling okay? So my notation is a little bit different from the way it's written on the equation sheet, but they're essentially the same equations. And then did we write a fourth one up there or no? Did we? I can't remember if we did that yesterday or not. We did not. Okay. So the other one, the one that we developed that we had to use last time was, how did we write it down? I can't remember. Was it delta x? Plus 1/2 change in velocity. Yeah. And it's actually, I misspoke before. It's actually VF plus VI, because really what you're doing is finding an average. I misspoke on Friday and I wanted to double check that, which is part of the reason I'm glad we're doing this. Okay. So the average speed is equal to the average, or excuse me, average velocity is equal to the average velocity. Okay. So that, to be very clear, that's what we're talking about there. Okay. And just to make my life a little easier, I'm just going to number these. They're in really no particular order except the order that I wrote them down in, mostly because I don't want to rewrite them. Well, I don't know. We'll see. I'm going to make a chart like this. We'll just go like that. Bam. Bam. And there are 5 different variables that you might find in these. Initial velocity, final velocity, acceleration, time, and displacement. I didn't write those in any particular order, just the order they popped into my brain. Just going to draw a nice cute little chart here. I like to do this to gain an appreciation for what each of these equations has to offer you. Okay, each one has something different to offer. I'm going to look at number 1 together right now. It includes VF, so I'm going to put a little check mark. Yep, we've got VF. It includes VI. Yep, we've got VI. It includes A, and it includes T. There is no delta X in that equation. See what I'm saying? I'm going to give you just a moment. You and your table mates can work together. If you want to do it by yourself, you're welcome to as well, to fill in the other 3 rows. Go ahead and do that. This is one of those things that, again, is not something that you have to have memorized. but it's just kind of a nice. So let's go through these now. So in equation 1, the thing that does not exist is the change in position, right, or displacement. In the second equation, what isn't there? What's missing? Final velocity. How about the third equation? Time is not there. And what are we missing in the fourth equation? Acceleration. So if you look carefully at this, you'll notice that every equation has something different that it's missing. Every equation has VI, okay? So that's one thing you're going to have to know. I mean, there are ways to manipulate things, but generally we don't want to have to do that, okay? But using this chart to kind of help, you can figure out which of the 4 equations is going to be your best bet on any of the problem-solving things that we do, okay? So I'm going to jump over to the other page for just a second. I'll come right back, okay? So I'm going to look at this. Looking at this pink list here, I've got time, acceleration, initial velocity, and displacement. What thing do I not have? Final velocity, right? So if you look at your chart, that's going to help you to figure out which equation you want. So take a look at your chart again. So I'm looking for something without final velocity because I don't care about final velocity. Which one is a good choice? Number 2. Does that help? Does that kind of make sense? That's my goal. My goal is just to help you out. This is not like something to memorize. It's just something to kind of help you as you're getting started. So we're going to use equation number 2 to solve that problem. Okay? So I'm going to jump back there. That's the big long one. It's my favorite. It'll be your favorite eventually too. Sometimes it just takes a little time. All right, so let's find out the displacement. So I've got my delta x is equal to VIT plus 1/2 AT squared. Hey, this is nice because I don't have to do anything. No algebra necessary, right? Plug it in and go. Don't forget your squared. If you haven't done so already today, which I'm guessing you probably haven't because I don't see any calculators out, get out a calculator right now. Again, even if you've done this before, it never hurts to do a little bit more calculation just to double check. So I've got my givens, my unknown, my equation. I'm going to substitute. Oh, that goes away. See ya. That's nice. Bye-bye. And then you can just do 1/2 times 1.5 meters per second squared times 5 seconds quantity squared. You plug it in. Everybody gets to do it on the calculator. You get to do it. You get to do it. And you get to do it too. Yay! Does anybody need a calculator? I can help you out. You got fancy purple calculators? Anybody else want one? Whoa! Yeah. Once you got the answer, check with your table. Do they agree with you? What did you get for that? How far did it go during that first part? During part A? 1/2 times 1.5 times 5 squared. 18.75 is that what you said? Can somebody corroborate that? Did you say 18, Ira? 18.75, okay. I just had it in my head and I couldn't remember for sure. 18.75 meters. Check those units, make sure they work. Meters per second squared times second squared. Second squared, bye. Meters is all that's left. Okay. Are we done with the problem? No, that's not fun. Of course not. Now we need to figure out, well, we found the displacement here. We need to find the displacement for part B. So I've got acceleration, time, and displacement. Are 3 things enough to use any of those equations? No. I need to know something else. What is the something that you always need to know? The initial velocity. How are we going to find the initial velocity for part B?
We take the initial velocity from part A and we can find out what it is after 5 seconds.
Does it make sense, friends, that the final velocity from part A is the same as the initial velocity for part B? Okay, so they're I don't want to say tricking us. They're just squeezing an extra little problem in there. And actually, that is the question that we answered in this. Actually, no. Sorry. I thought that they were being tricky, but they really weren't. All right. So we need to find a final velocity for part A. Do you have an equation that includes T, A, VI, and VF? Let's check. T, A, VI, and VF. Oh, it's there, right? It's right there. T, A, VI, and VF is right there. It's that first equation. So let's use it. Let's do it. So our equation is, what is it? VF is equal to VI plus AT. VI is 0, so that's nice. That's a good deal. So the final velocity for part A is going to be equal to, what is it, 1.5 meters per second squared times that 5 seconds. Maybe you can even do that in your head. I don't know. Oh. And if you can't do that in your head, it's okay. No judgment. It's all good. Sometimes it's just good to try and get that mental capacity in there. So now I've got a VF. But VF for A is, what did we say? The initial velocity for part B. So I'm going to throw it over here. Is 7.5. That was kind of ugly, sorry. Okay. Can you do it?
Yeah.
Do it. I'm going to let you guys work for a second. Then we'll keep cruising. So to find so you're trying to just figure out how we got this? Is that what you're saying? So in order to do that, I'm going to look at what I know. I know these three, and I want to find this one. Is that okay? So I'm going to look at my chart and look for T, A, VI, and VF. Is that okay if I jump to the chart? T, A, VI, and VF. Chart. T, A, VI, and VF. That's that first equation. So I'm going to use this one. Does that help a little bit?
Yeah. How does it give you A?
Because I'm just talking about, so all of these givens in pink here are just the part A. You can say no, or you can say yeah, it's okay. All of these things right here are all just for part A. So I'm just finding the final velocity for part A. How's that feel? And is that good or not okay?
I think so. Yeah.
Yeah. So that's going to tell you the final velocity for part A. The end of part A is the beginning of part B. So I can plug it in over here. I don't know if I'm just saying the same thing over and over in a different way that's not making sense though.
No, I hear you. Yeah.
Is that okay? Okay. Yeah. Yeah. And friends, I do want to say that kinematics problem solving, that's what we're doing right now, is kind of challenging. Especially like for some people, it's just hard to see it. And I'll tell you who it was absolutely challenging for. This girl. Okay. It was hard. It still is kind of hard. So I don't want you to feel like, wow, I'm the only one that can't do this, because you can absolutely, it just might take a little time. And that's okay. All right? I'll help you. I made it through. You can too. Now we're going to take a look at these things. Which equation do we want? Number 2, my favorite one, right? Displacement is equal to VIT plus 1/2 AT squared. I do love it.
Yes.
So that's going to be 7.5 meters per second times 3 seconds plus 1/2 negative 2.0. That negative matters because we're slowing down, right? Times 3 seconds squared. Do we get an answer for this part? Yeah? What kind of number did you get? What was it? 13.5? Okay. That's not me being critical. That's me just making sure I can hear. Can anybody corroborate that? Anybody else get that number? Yeah? So even though Eden didn't ask for it, we actually did. No, we didn't. At the end of the breaking period, we didn't do that. I keep thinking we did. How far has it gone? It's going to be 18.75 plus 13.5. Yeah? Add them together and you get? Yay! They just rounded because they only had 2 sig figs because they were being good sig fig kids. But you can leave it in the nice happy way if you want. That was tough, yeah? You got it though. Are there any others of these that you want to go over right now? Couple of things I want to tell you about this real quick. Kinematics problems are important. We're going to talk about some different approaches to them throughout the next couple of days. But I want you to know that on the AP exam, they almost never give a problem like that. They almost never give a problem that hard and in depth. They used to, okay? 6 years ago, before they had done the redesign, there was absolutely problems like that all the time. But now they want you to understand the way things happen. So the questions that I asked leading up to this, like, is it going to be going faster or slower? Is it going to be going positive or negative? That's what the AP exam is going to look for. That's the kind of stuff that I'm going to look for on a test or a quiz, okay? So a question that deep and that involved, not going to happen. Or if it does, it will be scaffolded step by step by step. How fast is it going now? Is it going forwards or backwards? Like, it's going to be scaffolded more. Does that make sense? So the reason I tell you that is that I don't want you to get scared by a question like this, okay? We do the hard stuff in class together so that when you take a quiz or a test in May, you're ready to go, okay? Questions right now? If you're overwhelmed with this, if you need help with it, you just let me know. Come talk to me and we'll do it. I can spend lots of time doing kinematics problems anytime you want. All right, it is time to go over your AP workbook, sheet 1H. Why don't you get that one out real quick? Whew, we're just like ticking things off the list today, friends. Great. All right. Yeah. Soon? I don't know for sure. Yeah. Yeah. Yes, please. That would be perfect. Yep. If you need a pass, let me know. Yep. Yep. I'm going to repeat that to everybody. Is that okay? The question, friends, was if you wanted to do corrections on your quiz that we had last week or whenever that was, okay, you can come in. Remember we talked about corrections and all that stuff. I would like those to get done this week. So unless that totally doesn't work, and if it doesn't, then you're going to talk to me this week so we can arrange for next week. But Liberty time is a great time before school. After school, a little less so, but talk to me. If you have a free period, you can come in and you can either, if I'm free, you can work out here or you can work in the back room. Okay? Lots of options, so make sure you make it happen. Okay. You all worked on this while I was away. Do you need a moment to review and to discuss, or are you ready to just jump in? A moment to review and whatever? Yeah, do it. Make that happen. Take a moment to review. Look over it. Let's do it. Okay. So this scenario shouldn't be too far from your brain given what we just talked about, kind of what we've been doing all day. It says the motion of a car starting from position x is equal to 0 meters is modeled in the velocity versus time graph at the right. Using the equation for a line y equals mx plus b, write an equation for the velocity versus time line given above. Now, even before we do that, tell me what's happening with this car. What's it doing? Slowing down? So it starts off at a position of 0, but does it start off from a velocity of 0? No. So it started off somewhere else, but when it crossed that line, that starting line, whatever we're going to call it, it was moving pretty fast. And then it's going to slow on down. Yep. All right. Now, it slows down. What happens right there? Starts going the other direction. Does that make sense? Because you've got a negative velocity. That's just like keeping in our brain. And I know it gets into that. I just want to make sure we're looking at it and thinking about it in a clear way here. All right. So, what do we say here? Who's got this? You guys all said you were ready to go. This is the last thing Chris gets to tell me. Go, Chris.
-4 n plus 12.
-4 what?
X plus 12. I put the n instead of, yeah, it's x. That's what, -4 x plus 12.
Okay, what's on the x-axis?
Oh, I just put that down in.
Time. That's okay. That's why we're talking about this. And so I've got some more stuff here. And so I appreciate your kind of getting me started here. Oh, and you said plus 12, is that right? Okay, sorry, I missed that part. Okay, so a couple things that I'm missing. I'm missing a letter over here, and I'm missing some units over here. So can you help me out with that? So V, you said?
Yeah, so it's,
What are the units of this thing going to be? And I'm not putting Chris on the spot. I'm asking everybody.
meters per second squared.
Meters per second squared, because this is the slope, right? Slope is changing y over change in x. You've got meters per second, meters per second squared. Okay? You can get so very darn much from the graph. What's up?
Why is it negative?
Why is it negative? That's a really good question. Because we just trust Chris, and if he says it, it's got to be true. Is
Yeah,
that?
it definitely is 1. I don't know why I had 4.
I don't know.
Yeah, it's definitely 1.
It's definitely 1.
Yeah, no, it's 1. Oh yeah, the units are big. Yes, the units are big. That's why. I like this.
Okay.
The graph.
I don't want to put you on the spot anymore, Chris, because I
Each
feel like it's
square
kind
is
of.
4 units. That's what it is.
Let's talk, shall we? So where in the world are you getting this for? What part of the graph are you looking at?
I'm looking at what's the word? A y-axis.
Okay.
It's incrementing each line is for each place on the thing is 4. Like it goes 0 to 4.
Okay.
12. So it's each square is then 2 because it goes like each line.
Okay, I'm going to back you up for a second. I want to know from a fundamental level, why are you why are you talking, like, what about this graph is leading you to a 4? What part of the graph? By that I mean, like, is it a slope or a y-intercept or a blah, blah, blah? The slope. Okay, so let's look at the slope, right? Because again, they say here, y equals mx plus b, right? So this is your y. And so then your m is going to be change in y over change in x. Is that okay? Change in y. So now we're going to talk about the scale, right? So 12 to 8. And so that goes, so they're each by 2, right? So 2, 4, am I counting this right? 6, or I could go all the way down. Maybe I'll just go all the way down. That'll be better for counting's purposes. So that's a change of negative 12 is my delta V meters per second. And at the same time, I've got a change in X, or my time goes from 0 to 3 seconds. Is that okay? So negative 12 divided by 3 gives me negative 4. Does that make sense? It's all about the scale. And sometimes, friends, I always really appreciate questions. Sometimes people ask questions like, oh yeah, I see. But it's really important to engage with it, even if you know that answer is right, because it's important to know why it's right. So yeah, the negative 4 comes from the slope. Bam, it's there. And then you've got the t, because that's like your x. And then what's this thing? It's 12. It's the y-intercept, but it also needs some units. What units am I going to put on that one? Okay. How are we doing? Is that okay? This should not be super scary, but I want to make sure you know. It says the slope of the velocity versus time graph represents that. We've only said it a few times yet. What is it? Acceleration. All right. Oh, Carlos, I will tell you, friends, you will learn to love, maybe not, learn to anticipate these kind of problems. AP loves these. This is what some student says. Are they right or are they wrong? Right? And figure out why. Carlos makes the following claim about the motion of the car. The car is slowing down for the entire distance it travels because the slope of the line is always negative and never changes. So let me ask real quick. Is the slope of the line always negative and never changes? Yes. Does that mean that the car is slowing down for the entire distance? It doesn't necessarily mean that, right? That's what we just saw when we looked at this fact that it crosses the axis. Right? So just keeping that in mind here. Evidence, fill in the blanks, blah, blah, blah. It starts off with a velocity of, help me out, table 1. What you got? Starts off with a velocity of 12 meters per second and is slowing down or speeding up. We're right here. Slowing down for the first 30 seconds and then speeding up. So the speed increases. The velocity continues to decrease, but it's just getting more negative, right? At 3 seconds, the car's motion changes from traveling in the, what'd you guys say back there? So we're right here. Car's motion changes from traveling in the blank to traveling in the blank. Help me out, back table. We agree? Yeah? Okay. And then the horizontal intercept represents the blank. What did you guys say up here? The time? When Eden, what would you guys say? The velocity is equal to 0. The car accelerates constantly with a magnitude of meters per second squared because the slope of the line never changes. Eden, what's up, my dear?
Why is it speeding up?
Why is it speeding up? It's a very good question. I'm glad you asked. Are you asking like physically why is it speeding up or how do I know that it's speeding up?
How do you know?
I'm going to open that to everybody. How do I know it's speeding up?
Is it positive? Well, that's like, in my brain it does, but like really it doesn't. But if it goes the other way, it's going. It makes sense in my brain.
No, it's okay.
If it's going backwards, it's still
Below 0, so that means going in reverse.
I get that it's going in reverse. I just don't know why it's speeding up.
What's the difference between velocity and speed? Velocity includes that direction, right? So a negative velocity tells you what direction it's going in, right? The speed is the absolute value. So if you go more negative or more positive, you're still speeding up. Does that make sense? So if I get in a car and travel at 30 miles an hour this direction, and Morgan gets in a car and travels at 30 miles per hour that direction, we both have the same speed, but we do not have the same velocity, right? One would be positive, one would be negative. And that's what's kind of going on here is that we have a positive velocity, 0. And then we have a negative velocity, but that negative velocity keeps getting bigger, more negative, further away from 0, faster and faster and faster.
Well, why does that mean if it's the same slope, then why is it a different speed?
Because this is a velocity versus time graph. We'll come back to it tomorrow. Does that sound okay? Eden, will you write that or put a star by that so that we can talk about it first thing tomorrow? Does that sound okay? You do have homework for tomorrow. We'll go over a bunch of homework tomorrow. Sounds good? Bye.